The dusty gas model provides a framework to describe the transport of gaseous components inside porous materials. The applicability of the dusty gas model is restricted to pore diameters larger than 2 nanometers, i.e. mesoporous and macropores, and not micropores. The textbook by Mason and Malinauskas is the standard reference material for the dusty gas model. This book was published in 1983. In the classic dusty gas model framework, the molecule wall collisions are described by concepts that trace back to the work of Martin Hans Christian Knudsen and the use of the Knudsen diffusivity. As a special case of the dusty gas model, we may derive the Graham's law of diffusion. Thomas Graham was a Scottish chemist. The objective of my presentation today is twofold. I use the generalized Maxwell-Stefan description to derive the dusty gas model and test the applicability of the dusty gas model using published experimental data. The material I will present is largely based on the 2 publications listed here. Watch also my presentation entitled Investigating the Validity of the Knudsen Diffusivity Prescription that is available on my YouTube channel. Another video titled Uphill Diffusion is also relevant to the following discussions. To keep matters simple, let us begin by looking at diffusion of a mixture of 2 gaseous components inside a porous material. In the Maxwell-Stefan formulation for diffusion in the system, we consider the porous material to be a pseudo-species in the mixture. In a sense, we treat the wall as large giant species fixed in space. So these are the rose-colored spheres shown here. The black and the blue spheres are the 2 gaseous components. In the Maxwell-Stefan formulation, we assert that the force acting per mole of species I, which is the negative of the chemical potential gradient, is balanced by friction. Component 1 experiences in undergoing a relative motion with respect to species 2, and the friction it experiences in undergoing relative motion with respect to the 3rd component, which is the pore wall. The relative motions are described by the difference in the velocity u1 minus u2, and since the wall is stagnant, we just have u1 here. The multiplier here is a kind of a drag coefficient, and the frictional term for species 1 with respect to species 2 contains a multiplier which is the mole fraction of component 2, because the 1-2 friction depends on the amount of 2 with respect to component 1. The Maxwell-Stefan diffusivity D12 has the physical significance of an inverse drag coefficient. For an ideal gas mixture, this coefficient can be predicted to a high degree of accuracy from the kinetic gas theory. The coefficient D1W reflects molecule wall collisions, and this diffusivity is Knudsen-like in character. Indeed, for a set of conditions that are necessary to abide by, this diffusivity may be identified with the Knudsen diffusivity. Similarly, the force acting per mole of species 2 is balanced by 2-1 friction, and the friction component 2 experiences in undergoing relative motion with respect to the wall. Since the wall is 0, we just have the velocity component 2 here. D21 equals D12 because of the Onsager symmetry relations. We may recast the Maxwell-Stefan equations in terms of molar fluxes. These molar fluxes are expressed as moles per square meter of pore area per second, and that is equal to the molar concentration of component I within the pores times the velocity of component I. The molar concentration of species I for an ideal gas mixture is the partial pressure of species I divided by RT, and for an ideal gas mixture, the gradient of the chemical potential is RT times dln of the partial pressure of component I. With these substitutions, the Maxwell-Stefan relations are rewritten in terms of the gradients of the component partial pressures and the molar fluxes of N component 1 and 2, N1 and N2. To repeat, D12 and is the diffusivity of the component 1, 2 in the bulk gas mixture. D1W identifiable with the Knudsen diffusivity for conditions where the Knudsen prescription holds. If we add the left members, we obtain the gradient of the total pressure, P1 plus P2, and these two terms on adding cancel each other out, and we will have simply the flux of component 1 divided by the coefficient D1W plus the flux of component 2 divided by D2W. Before proceeding further, let us get a feel for molecule-molecule and molecule-wall collisions by looking at animations obtained from MD simulations. We look at diffusion of hydrogen inside a 4 nanometer mesopore. The hydrogen molecules collide with other hydrogen molecules. They also collide with the wall. On colliding with the wall, a hydrogen molecule gets reflected. We now look at the motion of methane molecules. There is a stark difference between the motion of methane molecules in comparison with the hydrogen molecules observed earlier. The methane molecules on colliding with the wall stick to it and have a tendency to move along the wall before returning to the bulk. So you see a higher concentration of methane near the pore wall surface because of stronger adsorption on the pore wall. So to differentiate between the characteristics of diffusion of hydrogen and methane, we look at the cartoon here. Hydrogen on colliding with the pore wall undergoes diffuse reflectance, which is a term that indicates that the angle of incidence bears no relation with the angle at which the molecule gets reflected. Methane molecule on colliding with the wall has a tendency to hop to a neighboring site before returning to the bulk gas phase. So there are fundamental differences between molecules that are poorly adsorbed and molecules that are strongly adsorbed. The Knudsen diffusivity prescription for molecule wall collisions is given by this formula derived by Martin Hans Christian Knudsen, a Danish physicist. The Knudsen diffusivity is equal to the pore diameter divided by 3 times the square root of 8 times the gas constant R, temperature T by 3.14, and the molar mass. Remember, the units here are in SI units. The formula is applicable provided the gas molecule undergoes diffuse reflectance on striking the pore wall. It is not applicable, as we shall see later in this presentation. It's not applicable to components that adsorb more strongly and have a bias to move along the wall. Let us examine the special case in which the total pressure is constant along the diffusion paths. For binary gas mixtures, the dusty gas model derived 3 slides ago yields the gradient of the total pressure is equal to the flux of component 1 divided by the Maxwell-Stefan diffusivity D1W plus the flux of component 2 divided by the Maxwell-Stefan diffusivity reflecting the collision between component 2 and the wall. If we apply the Knudsen prescription to describe the component Maxwell-Stefan diffusivities D1W and D2W, we have, for the special case where there is negligible gradient of total pressure, that the ratio of the flux to the flux of component 1 to the flux of component 2 is the negative of the diffusivity of component 1 with respect to the diffusivity of component 2. And in view of the Knudsen prescription, this is inversely proportional to the square root of the molar masses of component 2 to the molar mass of component 1. This is the Graham's law of diffusion that was derived by Thomas Graham, the Scottish chemist. We test the accuracy of the dusty gas model by examining experimental data for diffusion in a ternary gas mixture of helium, neon, and argon inside cylindrical capillaries. The capillary diameter is 39.1 micrometers, and the length of the capillaries are 960 micrometers. The experiments were performed in such a way that the pressure drop across the capillary was maintained to be 0, and therefore there is no viscous contribution to the fluxes. The compositions in the upstream compartment and downstream compartments were varied, but the total pressure for any set of experiments in the upstream compartment was maintained the same as the pressure in the downstream compartment. The fluxes of components 1, helium, component 2, neon, component 3, argon, are plotted here as a function of the average system pressure for the various sets of experiments. In view of the fact that the total pressure gradient is 0, we have this expression from the previous slides where D1W, D2W, and D3W are the Knudsen diffusivities of components 1, 2, and 3. The calculations of the dusty gas model are shown by the continuous solid lines, and these are in excellent agreement with the experimental data. The Knudsen prescription works well for inert, poorly absorbing gaseous species, as is the case for helium, neon, and argon that have poor absorption strength inside the glass capillaries. We now examine a set of experiments reported by Tushlinsky for description of the experiments and analysis. Refer to my paper published in Industrial Engineering Chemistry 2016. The experimental setup is shown schematically here. The upstream compartment and the downstream compartment are separated by a mesoporous membrane, and the pore diameter is 4 nanometers. We have a binary mixture in the upstream compartment and a binary mixture in the downstream compartment containing the same two species. The upstream compartment works under through flow conditions, and the total pressure is maintained at a constant composition at a total pressure of 100 kilopascals. The downstream compartment is closed entirely with no inflow or outflow, and initially it is maintained at 100 kilopascals. The initial compositions in the upstream and downstream compartments are different. What is done is to experimentally monitor the total pressure in the downstream compartment as a function of time. So let's look at two sets of experiments indicated by the circles and the squares. The circles represent a set of experiments in which the upstream compartment is helium, and initially the downstream compartment contains argon. So what happens is, this is a through flow of helium, and the helium diffuses very fast into the downstream compartment, with a consequence that the pressure increases, and this pressure increase is monitored as a function of time. And we see there is a peak, and eventually the pressures will equilibrate to 0 at long times. In the second set of experiments, the incoming gas is pure argon, and the downstream compartment initially contains pure helium. So helium diffuses out of the downstream compartment, and therefore the pressure reduces, and there is an undershoot in the pressure, and that also equilibrates at long time to produce a value of 0. The continuous solid lines are the calculations of the dusty gas model. In this case, viscous flow is negligible, and we take the Knudsen diffusivity to reflect molecule wall collisions. We see that the Knudsen prescription works very well to describe the transient counter-diffusion phenomena, because both components, helium and argon, are poorly adsorbing. Here I show 3 additional sets of experiments in the same kind of an experimental setup as described in the previous slide. Here is counter diffusion in a mixture of nitrogen and helium across a mesoporous membrane with a pore diameter of 4 nanometers. The experimental data shown by the circles and squares are in excellent agreement with the dusty gas model using the Knudsen prescription. Here we have experimental data for a mixture of helium and argon across a macroporous membrane of 100 nanometer pore size. The experimental data shown by the circles and squares are again found to be in excellent agreement with the dusty gas model prescription, accounting for molecule-molecule and molecule wall collisions, and the molecule wall collisions being quantified by the Knudsen prescription. Same membrane, a macroporous membrane with pore diameter of 100 nanometers, a mixture now of helium and nitrogen. Data in excellent agreement with the dusty gas model for molecule-molecule and molecule wall collisions following the Knudsen prescription. The simulations are described in my paper from 2016. Here are the experimental data for the transient pressure development in the downstream compartment for counter diffusion of helium carbon dioxide mixtures at 293 Kelvin and 343 Kelvin. The 2 compartments are separated by a 4 nanometer mesoporous membrane. The experimental data shown by the circles and squares are not in agreement with the calculations from the dusty gas model. The reason for this is because the Knudsen prescription used in the dusty gas model calculations does not hold for CO2 wall collisions, because CO2 is strongly adsorbed at the wall, and the effective Maxwell-Stefan diffusivity describing CO2 wall collisions is lower than the value anticipated by the Knudsen prescription. Here are experimental data for binary counter diffusion of mixtures of CO2 and propane. This mixture is rather unique in that the molar masses of CO2 and C3H8 are almost exactly the same, 44 grams per mole, and therefore, according to the Knudsen prescription, the molecule wall interactions of both components are identical, and for counter diffusion in this mixture, there should be no pressure increase or decrease for any mixture composition. So the dusty gas model predicts a 0 increase or decrease in the pressure in the downstream compartment. Experimental data, on the other hand, shows that there is a finite pressure increase or decreasing depending on the compositions in the up or downstream compartment. This failure of the DGM, dusty gas model, in these three examples can be ascribed to the fact that the Knudsen prescription overpredicts CO2 and C3H8, and the adsorption strengths of CO2 and propane are not exactly the same. Consequently, the deviations for the dusty gas model are different in these two scenarios. Further explanation of the quantification of these experimental data is available in my 2016 paper published in Industrial Engineering Chemistry Research. Watch also my presentation investigating the validity of the Knudsen diffusivity prescription on my YouTube channel.